Alright, this is lab 3, which is black hole. So, introduction. What is the problem we're talking about here? There are two parts to this lab. The first is finding the mass of the black hole given the mass of a star orbiting it, and the second is finding the initial velocity that a spaceship must leave a planet orbiting a black hole in order to not crash into either the planet or the black hole. Why are we interested in this answer? This lab is going to teach us more about the forces of gravitation and Newton's second law, and how to solve for unknowns concerning these problems. So a quick summary of our results. The mass of a black hole can be found by estimating a change in velocity given position changes, estimating a change in momentum from the velocity change, and then using Newton's second law to find the net force and the gravitational force equation to solve for the unknown, the mass of the black hole, which I will show you in the computational model. And the second part is the initial velocity of a spaceship about to take off from a planet must be found by calculating all the gravitational forces involved, along with using both velocity update and position update formulas for both the planet and the ship. And that will also be in the second computational model. So our fundamental principles, right here we have the formula for velocity, which is change in position divided by change in time. We have the rate of change of momentum, which is change of velocity times the change in mass. And then we have Newton's second law, which is F equals dp dt. Our gravitational force formula, which is negative g times the mass of one object times the mass of second object divided by the distance squared between them times r hat. Then we have our velocity update formula right here and our position update formula. So part 1, finding the mass of the black hole. So here's the code that we use to find the mass of the black hole. Now you see up here, here's that gravitational constant, 6.7 times 10 to the negative 11th, as well as the mass of the star, which is 2 times 10 to the 30th. Our delta T is 86,400 because that is how many seconds are in a day. And then as we continue over here, we have our initial momentum, which is the mass of the star times the velocity initial, and our final momentum, which is the mass of the star times the final velocity. We got our change in velocity, v final minus v initial, our change in momentum, p final minus p initial, and dp dt, which is our net force, which is going to be the change in momentum divided by the change in time, and that is our f net. And then down here as well, we're also finding our parallel and our perpendicular forces that we're going to show in that computational model with this line of code over here. And then our mass of the black hole, we manipulated the gravitational force equation to solve for one of the masses. So when you manipulate it, it comes out to F net times the position of the star in between squared, which is our r squared, divided by the gravitational constant times the mass of the star. And then we're just going to go ahead and print that. And then over here we have our arrow scale. This is just going to show us all of our nice forces. And let's go ahead and show you the video of that code when you run it. So right here you can see the parallel and the perpendicular forces as well as the net force with those three arrows. And it's just going to go right around that black hole. Awesome. And we're going to go back. So our mass of the black hole we found to be 1.01446 times 10 to the 34th. And so part 2, don't crash, is going to use that mass. So we are a spaceship on a planet orbiting a black hole, and we want to take off with enough velocity that we do not crash into the planet or the black hole. So for starters, we're going to put the mass of our black hole all the way up here that we just found. Here are other constants, which is just the mass of our planet, mass of our ship, gravitational constant, etc. And our ship speed x and our ship speed y so that we can get the velocity of the ship that we need. And so over here is where we're going to start our computations. So we want the force of the black hole on the planet. Now, once again, we're just going to use the gravitational force equation, which is seen right here. And then the distance, like the r value that we're going to find, is the planet dot position minus the ship dot position when it comes to the ship and the planet's gravitational force. And we can plug that in and use it for the force of the ship on the planet. And then we want the total force that is on the planet. So we're going to add the force of the black hole on the planet plus the ship on the planet. And then down here, we're going to do something very similar. We're going to find the net force on the ship. So first we're finding the net force of the black hole on the ship, once again just using that gravitational force problem. And down here we're also finding the force of the planet on the ship, again using that gravitational force problem. And we're just going to add this together to find the net force. Down here we have the velocity update formula for the planet, the position update formula for the planet, the ship velocity update formula, and the ship position update formula. So here is our computational model. We're now super far away from that black hole, which is perfect. So what does it mean? So the rate of change of momentum might seem equal to the net force because dp dt equals the net force, but it's slightly different because the rate of change of momentum is equal to the mass times the velocity. So the only things affecting that are the mass and the velocity. But our net force, on the other hand, needs to be determined using the gravitational force equation because those are the forces involved. So we need both masses, we need the distance between them, we need that gravitational constant, and we need r hat, making these two values very different. So what if we want to orbit the black hole, but we don't want to orbit the planet? So in order to orbit the black hole, the velocity needs to overcome the gravitational forces produced by the planet, but it can't overcome the gravitational forces produced by the black hole. So now we just have our general conclusions, same as our summary, and thank you so much for watching my video.